Hello, everyone. Today we are going to talk about the phase diagrams. Phase diagrams are one of the most powerful tools in material science and mechanical engineering. They show which phases exist in an alloy at different temperatures and compositions and helps us to predict how an alloy will behave under real-world conditions. In this video, we will focus on some binary alloys such as CuNi, copper nickel, and SPBI, exploring how to determine which phases are present, calculate phase compositions, and find weight fractions of each phase using the lever rule. We will also see how these phase fractions and weight percent directly influence properties such as mechanical properties or material properties like strength, tensile strength, ductility, and hardness. By end of this video, you will understand how to read phase diagrams and apply the lever rule to real alloys and connect these concepts to mechanical performance. This is the first part of this series, so make sure to watch all parts to get complete understanding of phase diagram and mastering in phase diagrams and their engineering applications. Okay, in this slide, we are talking about what is phase diagram. Phase diagrams indicate which phases exist depending on temperatures and conditions, and sometimes pressure. In these videos, we focus on binary systems that we have two components, such as, for example, here you see we have nickel copper, so our components are Ni and Cu, yeah? So they are binary systems with two components, and we usually keep pressure constant at 1 atmosphere, as you see here. The copper nickel phase diagram include two phases, the liquid that you see as a green color and solid phase that is alpha phase with FCC structures, phase center cubic. There are three regions. If you see here, the green one that is completely completely liquid, the blue region that's completely solid solution, and this area that is liquid plus alpha means we have two phases simultaneously, liquid and solid. Okay. What is isomorphous systems? Isomorphous binary phase diagram here shown for Cu and nickel system. It is called binary, as I explained in previous slide, because it has two components, copper, nickel. The system is isomorphous, means the two metals are completely soluble in each other in both the liquid and solid state. If you remember from the previous videos, we talked about that how many criteria we should have that we have the solid solutions. Our materials can solve in each other completely for reaching to isomorphous alloy. One of them means the difference in radius should not exceed 15%. Another electronegativity should be close, or structures should be close. Here we have all criteria for copper and nickel. So the system is isomorphous, meaning the two metals are completely solved in each other in both liquid and solid state. As a result, the alpha phase that is solid extended continuously from 0 to 100 weight percent. nickels means completely solved. We cannot distinguish, for example, its part is, for example, copper, it is nickel. Okay. Which phases are present in phase diagram by using the temperatures and C naught? So in this slide, we see how to determine which phases are present if we know the temperatures and overall or average compositions that we show as C naught. According to the rule 1, once T and C naught are known, we can locate the point on the phase diagrams and identify which phase we are. For example, at point A, that is 1160 weight percent nickel, we reach to point A, and you see it is exactly located in blue region, that is solid solution. But for point B at 1250 and 35% weight percent nickel, we reach to point B, and B is in liquid and alpha phase, means we have two phases simultaneously at point B, liquid and solid alpha. Rule 2. This slide explains the rule 2, which helps us to find the compositions of each phase when temperatures and overall compositions are known. For example, if the overall or average alloy composition C naught is 35%, and temperatures is 1320, we reach to point B, okay? We are at this point. It is fully liquid, so the weight percent of the nickel or the overall weight percent, both of them are same, and it's 35% nickels. When we are at the temperature at point D, 1190, and again, overall compositions percent or weight percent is 35%, we reach to point D. We are only solid phase, that 100% solid, and the composition weight percent in alpha equals to overall composition equals to 35%. But if we are at 1250 centigrade, and again overall composition same as A and D, we reach to point B. Okay, we are at point B. At point B, both liquid and solid alpha phase coexist. In this case, the compositions of the nickel in each phase different, but the average or overall is 35%. Okay, if we draw a horizontal line that in some textbook we say tie line, it intersects to two regions or two phases, liquid and solid, okay? They intersect the liquid at this point and read the compositions of this point, and it is 32. So the liquid has about 32 weight percent nickel, or Cl, or compositions of the nickel in liquid is 32 nickels. What about the, for example, Cu? For Cu is 68% Cu. And intersect tie line to solid region at this point, read the coordinate of this point, it is 43%. So weight percent of the nickel in phase alpha or in solid solution is 43% nickels, or 57% copper we have at alpha phase. So it is rule 2. Calculating phase fractions, how much liquid versus how much solid we have. So this slide explains Rule 3, which shows how to find the weight fractions of each phase using the lever rule. For two-phase alloys, draw a horizontal line that we say that the name of this line is tie line. At the temperatures across the, for example, two phases that we have, L plus alpha region. We are at point B. We draw a horizontal line across this region. The weight fractions of the solid alpha is calculated, or W alpha. I always say to my students in this trick, we have two length here, or two side here, R and S. Which of them far from alpha is R? So W, or weight fractions of alpha phase or solid solution, is the side that is far from that is R, per total length, that is R plus S. Or we can find R and S and R plus S by reading C alpha, C naught, and CL. Okay, what is R? As you see here, R is C naught minus CL. What was CL? When tie line intersect the liquid region, read the composition weight percent of that point, it should be CL. Intersect the solids region, read the composition weight percent of that point, it should be C alpha. So R, as you see, is C naught minus CL. What is S? Is C alpha minus C naught. What is R plus S? It should be C alpha minus CL. So substitute here, and we find that omega L, or weight fraction, or phase fractions of liquid, is 73%. And for phase alpha is 27%. Always should be 100. If we only have two phases, yeah, the summations of fraction weight for both of them should be 100. But if we have three phases, the summations of all phases that we have should be 100%. Okay. This slide explains the lever rule again, which helps determine the weight fractions of each phase in two-phase alloy. In this phase diagram, a tie line that is horizontal, and I explained you in previous slide, at a given temperatures, connect the composition of the liquid and solid phases in equilibrium. We write that again, if you remember, for W alpha, which side far from that, it's R per R plus S. And I explained to you how R is C naught minus CL, and S is C alpha minus C naught, and R plus S is C alpha minus CL. And here you see the lever, what fractions of each phase. Think of the tie line as a lever. So means that the moment they created, the M alpha times S equals ML times R, and we reach to this equation. Okay. This slide shows the cooling of the copper nickel alloy with 35 weight% nickels and the macrostructural changes that occurs. Look at here, at point A, we are 100% liquid, that you see green, yeah? By cooling and reaching to B point, B is the border that after that we have L plus alpha, means liquid and solid phase. You see the dark blue dot or spots here. These dark blue dots are solid phase, that is alpha phase, okay? When we are in liquid, the compositions weight percent of the liquid and the overall equals each other, and you see it is 35 weight percent. When we reach to B, we have some phase that is solid or alpha phase, and the majority of that is the liquid phase, and you see the small dot or dark blue spots that you see here. But the weight percent is different. Look at here. It is a tie line, yeah? Tie line intersect the solid at 46 and intersect the liquid at 35. So weight percent of the nickel in liquid is 35 and in solid is 46. Okay. Again, cooling and reach to C. When look at the C, the size of the grain bigger here, yeah, more solidifications. And again, draw a horizontal line or timeline, intersect the liquid at 32 and intersect the solid phase as 43. So at the liquid it's 32 and in phase alpha we have 43% in nickel. Yeah. Again, cooling up to reach to D. Again, draw a horizontal line or tie line, intersect liquid region 25, solid region 36. So 36% of the nickel here is in alpha and 24% in nickel we have in liquid, but the overall for all of them is 35%, yeah? And when we reach to E, completely solid, you see that we only have dark blue and alpha phase, and it is the border of the grain that you see here. It is 100% solid, and the weight percent in alpha phase, the only phase that we have equal to overall, that is 35%. Okay. During the solidifications of the copper-nickel alloy, if, for example, nickel be 35% that you see here, at 1300, the alloy is fully liquid, and around 1250, the first alpha phase appears. Here you see as point B prime, for example. If the cooling so slow, what's the meaning of slow means? Means 1 centigrade per minute. Atoms have time to diffuse. What's the meaning of diffuse? Means diffuse in other grains and producing a uniform alpha phase. If you look at here, all of them is dark blue. What's the meaning of dark blue? Means microstructure same, means the density same, means the weight percent of all layers same. But when you look at the right side, you see different colors of the blue, different layers. One of them lighter, at the core we have the darker. It means that more dense of the nickel we have at the core, and the other surface has less nickel. What's the meaning? That means that its cooling was so fast. The cooling rate, for example, is about 100 centigrade per minute or more. So diffusion is limited. So the first alpha to solidify is rich in nickel, 46%, as you see at the core, while the last alpha is poor in nickel, maybe less than 35% at the other surface, forming a non-uniform core structures. By 1190 centigrade, the alloy is completely solid, and difference in alpha composition inside grains reflect the cooling rate. So we expect that here we have the same microstructure, same mechanical properties, but here we don't expect that we have same properties at the core or other surface. Okay. In the Cu nickel or copper nickel system, mechanical properties change with composition due to solid solution strengthening. and it is very common for other alloys too, and it is the importance of phase diagram. For example, look at here. Here we have 0% nickel, but 100% copper. When we have 100% copper, means pure copper. It's so soft. Look at here, is 220, for example, tensile strength, but very ductile. How much ductility? About 55%. But by increasing nickel is added, nickel atoms cause the lattice distortion, making dislocation motion is harder. When dislocation motion is harder, it means increase the TS or tensile strength. And we see that increase up to peak here and about 450, and again decrease that tensile strength. But elongation decrease up to reach to minimum here, and after that a little increase that. So tensile strength is increased, but reduce elongation percent. TS or tensile strength reaches a maximum near 50% nickel, where the lattice distortion is strongest, while elongation percent reaches a minimum at the same compositions, means 50%. And beyond 50% nickel, we see that the TS slightly decrease or level off towards the pure nickels, and elongation is slightly increased, but remains elongation be lower than pure copper. And TS again higher compared to pure copper. In short, strengthening from nickel comes at the cost of the ductility, and the effect is most pronounced at intermediate composition. And here you see the table talk about the TS and elongation percent and what happens. Okay. Design. We are designing an alloy of copper nickel for strength and ductility, or targeted strength and ductility. In this problem, we are asked whether it is possible to produce a copper nickel alloy with a minimum non-cold work tensile strength of 350 megapascal. So 350 megapascal means should in this line. So in this region means appropriate for us, okay? And a ductility of at least 48%, 48% less. At least 48% means more than 48, it works for us, means here or here. So this region works for us, and this region for us. But here for tensile strength, this region for us. Okay, from the figure A, tensile strength greater than 350 megapascal is possible for compositions between 22.5 and 98%, as you see the region that I have shown here, okay, nickel. On the other hand, according to the figure B, ductility bigger than 48%, exit for composition less than 8%, here is less than 8%, and greater than 98%, and here more than 98%, and here between 22.5 CNOT and 98%. Okay. So therefore, the considering both of the criteria only met only on the compositions of 98 weight% nickel. Okay. Here, phase diagram of SBBI, and we want to, it is binary systems, binary phase diagrams. We have three phases, liquid, alpha, and alpha. And we want to talk about their macrostructures, level rule, and weight fractions, and review everything that we talked about that before. On the first one, we look at the SBBI alloy with the 8 weight percent SP and 20 weight percent bismuth. Okay, means here. We are here. Okay, sorry. We are here. Yeah. At these temperatures, the alloy is fully in the liquid phase. So what's the meaning? That means the weight percent in liquid and the overall same. At the overall, we had 80 SP and 20 weight percent BI. So it is equal what we have in liquid, because liquid is all and alpha none or 0%. It is 100% and 0%. Here we see the macrostructures. The blue one is the bismuth, and the red one is antimony or Si. But both of them in liquid phases, okay? On this slide, the alloy has cooled up to 5340 degrees Celsius. At this temperature, solidification begins, and we see a mixture of liquid and alpha solid phase. If I want to show you these circles, I change the color. Yeah, these circles are solid, and you see the border of the grain, yeah? And except that we have the liquid. So here we have liquid and we have alpha phase. How we can find the weight fractions of each of them? Easy. It is the tie line intersect this point. This point for this is 12. Yeah. Here you see 12 weight% BI in alpha phase, and this point is 45. Yeah, and this point is 20. Okay, so how much W alpha? W alpha is this region here is liquid. If you remember, I told that the side that is far from that. Which side is far from alpha? This side is far from alpha. So should be 45 minus 20 per total side should be 45 minus 12 times 100%. So W alpha here is weight fraction is 76%. For W liquid, you can say 100 minus W alpha because we have 2. Or if you want to write that, which side is far from liquid? This side. This side is 20 minus 12 per total. Should be 45 minus 12 times 100%. Okay. So W alpha is 76%. W liquid is 24%. And in this alpha, how much we have overall, not overall, the composition weight percent. So we have 12% BI and 88% SP. Yeah. And for this, for liquid, how much we have BI? We have 45 BI, and how much SB? 100 minus this, it should be 55% SB. Okay. And the last one, on the third slide, in this slide, the alloy has further cooled to 46 degrees Celsius. At this point, the alloy is fully solidified and consisting entirely in alpha phase or solid solution here. And the overall compositions equals to compositions at alpha phase. Here was 20, again it's 20 in alpha phase and 80% overall, and alpha is equals, we are 100% alpha and 0% liquid. Okay. And the last slide that is very important in my opinion. You remember that we talk about several slides, talk about SBBI alloy with 80 weight percent, SB and 20 weight percent bismuth at different temperatures from 100% liquid up to 100% alpha phase, and between them in liquid and alpha phases. Phases diagrams are critical tool in material engineering. Why? Because they show which phases are present at any given temperature and composition. By calculating weight fractions and composition in each phase, for example, you remember that when we are in liquid and alpha phase for SBBI, for example, in alpha phase, we have 12 weight percent BI, and we have, for example, 88 weight percent SP, and for liquid, I think 45, 55 somethings. So by calculating the weight fractions and composition in each phase, we can directly predict mechanical properties such as hardness, ductility, toughness. For our SBBI examples, knowing the phase fractions at these temperatures help us tailor the alloy for specific applications. Whether we need more strength or we need more ductility, as you have seen that we design one alloys of copper nickel. This is why understanding and applying phase diagram is so critical and important in materials and mechanical engineering. Thank you so much for watching this lesson on phase diagrams, the Lever rule, phase fractions, and weight percent calculations. If you found this video helpful, please like, comment, or subscribe to my channels, MechTalks 2025. And to follow the rest of this series by mastering these concepts, you can predict alloy microstructures and mechanical properties like strength and ductility, which are critical for designing safe and efficient material. The next video in this series will dive deeper into eutectoid alloys and show how phase diagrams guide mechanical property optimizations in complex systems. You can click the link on the screen to continue learning and strengthen your understanding of material and mechanical engineering. Thank you so much.